Alright, today we're going to be starting a new unit on probability. And as you can see from the slideshow here, we're only going to be dealing with known outcomes. A lot of the things we look at in life don't have known outcomes like this. That's why people like sports so much. You never know what's going to happen on any given event. Even a team that's not a great team can have a great day. So the things we're going to look at here on probability to start are all going to be things with known outcomes, things that we can count, things that are equally likely to occur. So if we look at my general intro here to a probability, you have to know two things. You have to know how many ways the desired outcome can happen, and you need to know how many total outcomes are possible. And we're going to turn this into a fraction. So you're going to have your favorable outcomes divided by the total outcomes. So a lot of the times when you're playing games and whatnot, you need a high roll. So lately, I've been playing a lot of Mario Party with my family, and you'll be looking for a particular type of roll. And you want to think, all right, should I use the 4, 5, 6 block, or should I roll all 6 dice? So you have to make these choices based on how many good rolls are there and how many total rolls are there. So that's how we're going to set up all of our probabilities. Now you're going to notice I say P parentheses event. The way I'm going to ask you for a probability or show a probability is using this capital P and then putting the condition inside parentheses. And then whatever you get for the answer will be written as a fraction. Now, I'm going to propose this following situation. Don't know how many of you have played dice games, but a 4-sided die is possible. We call them D4s. You also have 6-sided dice are common, 10-sided dice are common, 12-sided dice are common. So here we're going to roll a pair of D4s. And you may notice from the picture, this side of the cube only has a 2, a 3, and a 4 on it. But that's okay because the number on the bottom is a 2. So on all the faces of this die, there should be a 2 on the bottom. The same way that if the 3 were on the bottom, there would be a 3 on the bottom on the back face and a 3 on the bottom on the side face. So that it's always going to represent whatever number's on the bottom. So let's say we roll these two 4-sided dice, and we're interested in their sum. Well, if you are counting total outcomes, you can't just say 2, 3, 4, 5, 6, 7, 8. There's 7 numbers you can get, so it's out of 7. The problem with that is they're not all equally likely to occur. So in order to see why that is, we're going to have to either make a sample space or we're going to have to make a probability tree. So there's 2 different ways that we do probability, and I'm going to show you both of them. My favorite is the sample space, especially for the type of thing we're doing right now. And then the other option is probability tree, which you'll see a little bit later on. But the sample space, the reason I like it is because, first of all, it's visual. And second of all, it shows me all the possible outcomes. Now, in this instance, there's only 16 possible outcomes, so it was easy to make a sample space. If there had been 216 outcomes, maybe a sample space wouldn't be the best way to do this problem. So if I'm looking at my sample space, what I'm showing you is the first die roll could have been 1 through 4. And then I'm showing you the second die roll could have been 1 through 4 as well. So this box with the 2 represents a roll of 1 on the first die and a roll of 1 on the second die. Whereas the box down here says a roll of 2 on the first die and a roll of 3 on the second die. So that's how we're coming out with these 16 outcomes. Now you're going to notice they're not all unique outcomes. There were 2 ways for me to roll a 3. There were 3 ways for me to roll a 6. So if you just look at what you see there, 5 is the most common outcome because there was 4 different ways that I could end up rolling a 5 out of the 16 possible ways of rolling 2 dice. Now, like I was saying before, there's also a probability tree. So in my first roll, I could have gotten a 1, a 2, a 3, or a 4. Notice that those events, if I put a little fraction on the line, this was my chance of rolling a 1. So I have a 1/4 chance of getting this 1. And then after I roll the 1, There's 4 different things I could have rolled for my second die, so I have to extend, that's why we call it a tree, I have to extend a branch out for each outcome that could happen on my second roll. So what I end up with is 16 unique possibilities. I could have gotten a 1 and then a 1, a 1 and then a 2, a 1 and then a 3, a 1 and then a 4. Or I could have had a 2 on my first roll, and then a 1, a 2, a 3, or a 4 on my second roll. A 3 on my first roll, and then a 1, a 2, a 3, or a 4 on my second roll. So you can see that I still have 16 outcomes, but for the purpose of this, I don't have any sums. I still haven't figured out what any of my sums are. So I really wouldn't want to use the probability tree for this particular example. Although I could quickly see that each of these things is a 1 out of 16 chance of happening, it's not something that I really want to be going through and recording. It would be cumbersome for me to now look at this and say how many of these sums are 5, because then I'd still have to do all the math. I'd still have to look at it and say, oh, 1 plus 4 is 5, 2 plus 3 is 5, 3 plus 2 is 5, 4 plus 1 is 5. That's just tedious. So in this particular example, we're going to go with the sample space when we're trying to figure out what the sums are. So our basic things with probability is that if I'm going to make my actual probability, I can write it as a fraction, which is really helpful when I have a sample space, or convert it to percent if you're just trying to make a statement that relates to other people, other times. Maybe they'd rather have a percent. Maybe your average person doesn't see 3 over 16 and be able to make sense of that at all. So these could all be written as percents if you wanted them to. 3 out of 16, if I write it as a percent, would be 18.75%, almost 19% of the time. So you can convert these all to percentages. Now, if I try to make a conclusion out of it, I'm just going to ask some questions. We're going to talk about how we use the sample space to work backwards. The most likely outcome is a sum of 5, but even that most likely outcome only happens 25% of the time. Notice how I wrote the math. The probability of my condition, the sum is 5, is 4 over 16. Again, the reason I got 4 over 16 is because I had 1, 2, 3, 4 of the responses out of the 16 possible gave me a 5. So 4 out of 16 was my probability. Changing that to a percent, 25%. If I instead say I want a range of outcomes, I just have to add the individual outcomes. So if I say a sum of 4, 5, or 6, now I go back to my table. Anything that's a 4, 5, or 6 counts. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of my outcomes were a 4, 5, or 6. So you're going to notice that I have in my little slide here, 10 out of the 16 outcomes were either a 4, a 5, or a 6. That could be gotten by adding each of the individual probabilities together. 62.5%, just a little under 2/3. So you're very likely to roll 4, 5, or 6 when you're rolling 2 4-sided die. Now, let's say I don't want a sum. Everything I saw in my sample space was based on what the sum was. But you can still look at the outer blocks and see what we have. So if I say the probability that you get a pair, well, if I go back, even though these numbers don't indicate pairs, I can still say, well, a pair would be both die or ones. So I have 1 square which came from a pair. Here I have another square where I rolled a 2 with the first die and a 2 with the second die. So I have 1, 2, 3, 4 pair that came from those 16 outcomes. So I'm going to get 4 out of 16 being my answer. Now all of these could have been done using the probability tree, but it would have been a little harder. So if I'm looking for doubles in the probability tree, a 1 and a 1, a 2 and a 2, a 3 and a 3, a 4 and a 4, I can still see that 4 of my 16 outcomes down here involved a pair. Like I said, it would be harder to do the sums because it's just not set up that way, but it could be done. So when I look at this whole process and we say, what do I need to really know about probability? You need to know what your omega is. You need to know how many possible outcomes there are. In this example, I needed to know that there were 16 things for me to choose from. Even though there were only 7 numbers there, I still had 16 outcomes that I had to keep track of. The only other thing that you're going to want to pay attention to is if I gave you an or condition, where it's one thing or another thing, you just add those individual probabilities together. If I went back to this chart and just posed the question, what is the probability that I don't get a 5? Well, if you look at 5, I had 4 of them that came out to 5. Instead of counting all the other numbers that are in this spreadsheet here, I could just say if there's 16 total outcomes and 4 of them are 5, then 16 minus 4 is 12. We call that complement space. So the probability that I don't get a 5 is 12 over 16, because it's got to be the remaining part of 1. So I've already done, if we look at where I have right here, the sum of 5 is 25%. That means the sum is not 5 would be 75%, because that's the remaining part of 1. If 4 of the outcomes work, then 12 of the outcomes don't work. So that concludes all the things we're going to look at in the first part of probability. I hope that you found this helpful.